Section 16.3, the fundamental theorem for line integrals. Remember from first semester calculus, the fundamental theorem of calculus was if you have a definite integral, the answer is antiderivative of that integrand evaluated at the upper limit minus the lower limit, where f prime is continuous on a closed interval. Note, this integral was also known as the net change theorem. Besides fundamental theorem of calculus, it was also known as the net change theorem. Now, the fundamental theorem of line integral goes like this. Let C be a smooth curve. Smooth means what? The derivative of the parametric equations of the curve is not equal to zero vector for any t in the domain of the what? X and y components, or x and y and z components of the vector r. Given by the vector r of t, where t goes between a and b, let's say this is a and b, let f be a differentiable function of 2 or 3 variables. Remember, the function has to be defined and it has to be differentiable. Okay, now this would be a differentiable function of what? 2 or 3 variables whose gradient is continuous on curve C. Therefore, the line integral of f dot dr changes into, remember, we are seeking for what? Scalar functions whose gradient happens to be the same as the vector field. So we're going to replace the f with gradient of the lowercase f. Remember, this is a vector field. This guy is just a scalar function. So turns out this will give us, just like the fundamental theorem of calculus, just f, because that's antiderivative of derivative, of f evaluated at what? A and b, but in this case is what? The terminal side of the curve minus evaluated the what? Scalar function at the initial. The bottom line is the line integral, then it becomes solely dependent on the difference of what? Of the scalar function, which is known as potential function, evaluated at the initial and the terminal point of the curve, regardless of how we got from point A to B. That's why it's called path-independent line integral. Line integral. So the line integral is path-independent. What does that mean? We no longer care about how we got from point A to B. On which path did the object travel in order to get from point A to B? All we cared was what? Find that scalar function, which is called potential function, and evaluate it at the endpoints, and lo and behold, we have the answer for the line integral. So the theorem says we can evaluate the line integral of a conservative field. This is the definition of conservative field. That's like a vector field which happens to be a gradient of a scalar field. And that scalar function is called potential function, and the vector field in this case is called conservative vector field, simply by knowing the value of f at the endpoints of C. Because, so what happens is, if you are in 2 dimension, so this is the curve C, the path can also show up in 3 dimensions, so that would be like space curve, correct? Space curve. So the theorem says, look, if the vector field is what? Conservative, then in order to find the amount of work or energy which takes to move this what? Particle on curve C from point A to B, it is independent of how we got from A to B. We could have got to B via what? C1, curve C1, or C2, or C3. It doesn't matter because it could be any curve. As a matter of fact, when you have a conservative field, you don't have to know the parametric equation of the curve. It could be any path. All you need is to find the potential function, evaluate it at the endpoints. Lo and behold, you know the amount of work required to move the moving object from A to B along any path. So that's why it's called path independent. So in R2, the potential function will be a function of two variables. In R3, it will be three variables. So once again, what's the definition of path independent? So if you have a closed curve, okay, let's C1, C2 be two piecewise smooth curve like so. We say the line integral is path independent if the what? The line integral over C1 over path C1 is exactly the same as what? Over path C2 for any two paths C1, C2. Incidentally, piecewise smooth means what? You may have union of bunch of curves. Overall curve is not smooth because you got sharp edges here, but piece by piece they are smooth. So that's why it's called piecewise smooth. So the consequence of this story is we say that the line integral is conservative field. What? Of conservative fields are independent of the path. So the line integrals of conservative vector fields are what? Independent of the path. So if the curve is closed, then what? Then the line integral is zero. Why is that? Because what? C1 would be what? Line integral from A to B, right? C2 will be the line integral from B to A. These guys offset each other, and lo and behold, you have a zero. So the bottom line is this. If the vector field is conservative and the curve is closed, the amount of energy which takes what? To move the object from point A to B is zero. In other words, if the what? Curve is closed, so that means the initial point, what? Coincides with the terminal point. Therefore, the difference is zero. So keep that in mind. So, so the theorem is if you have a line integral which is independent of the path, okay, that would be independent of the path if and only if what? The line integral is zero for any closed path. By the way, this would be the notation for closed path on the integral sign. Do you see it? So the line integral can be zero even though the field is not conservative. Be careful. Sometimes you may get what? Zero line integral even though the what? Field is not conservative. So you may come across to that kind of scenario. Okay, let's define what they mean by simple curves. So these are type of curves. So a simple curve is a curve which does not intersect itself. If it intersects itself, it's not a simple curve. So this guy is simple but not closed. This guy is not simple because it crosses itself, not closed. This guy is simple and closed. It doesn't intersect itself, and notice there is no opening, so it's closed. This guy is not simple, but it's closed curve. It's not simple because it intersects itself, but there is no opening like this guy or this guy. So it's not simple, but closed. Okay, that terminology shows up in what? In the next theorem, so it'd be nice to know what a simple closed curve is. If the vector field is in two dimension with the x and y component p and q is conservative, then this is the test you apply to see if the what? field is conservative or not. In other words, if it is conservative, then this ratio has to be true, which is partial of the first component with respect to y. Is it equal to partial of the what? Second component with respect to x. Notice the order. This guy is with respect to y, that guy is with respect to x. If this equality holds true, then the field is what? Conservative. In other words, the field, what? Let F be the vector field on an open, simply, what? Connected region. So we're going to, what? Define that with P and Q being continuous first partial derivatives. And this, if this ratio proportionality is true throughout the region R, then F is conservative field. Let's define what they mean by simply connected region. Okay, so these are the type of regions which would be nice. They pretty much the topics of a course called topology. That's a graduate level math class. So these are the type of topics they talk about in that course. So the type of regions, so this is called simply connected region because there is no hole in it and it's closed. However, if there is a hole in the region R, okay, whether you have one hole or multiple holes, these are not simply connected region. This guy is simply connected, there is no hole, but it's open. Do you see it? Because it doesn't what? Include or contain the boundaries of the region. Do you see it? Okay, so here's an example. Question is, determine if this vector field is conservative or not. If so, find a potential function f such that f is gradient of that scalar function known as potential function. Immediately apply the test. Partial of p with respect to y, is it the same as partial of q with respect to x? In this case, we have a match, so the field is conservative. Therefore, what? The line integral, if you're going to perform the line integral over this vector field, it's going to be path independent. Because the field by definition is what? Gradient of a scalar field. So that means the vector field is what? The gradient of a two-dimensional what? Scalar function, namely f. But gradient of f is a vector whose components are partials. So that means what? This guy is partial of f with respect to x, and this guy is partial of f with respect to y. So what that means, you have what? Excuse me, two equations with partial derivative in it. So this guy is like partial derivative of f with respect to x. This guy is partial derivative of the same function with respect to y. So this is called partial system of partial derivatives. And the objective is to solve for what? Solve for f. So how do you do that? Select either of these equations, okay? Let's say equation number 1, and take the integral of both sides with respect to x. Remember, when you take the integral with respect to x, behind the scene, you are keeping the what? Y's constant. Therefore, this acts like a single variable equation. Therefore, I use dx as opposed to partial x. Do you see it? When you take the integral with respect to x by keeping the y's constant, you get this. But the constant of integration is not c, is a function of y. Why? Because we kept the y's constant, remember? So this is called constant of integration, but it's a function of y. Had you taken the integral of equation number 2 with respect to y, then your constant of integration will be a function of x. So here's what we have for f. Take the partial of this answer, number 3, with respect to y, get this. But now equations number 2 and 4, they represent what? The same partial derivative. Do you see it? Notice this is the partial derivative of the potential function, so is this. So they must represent the same, what, expression. So what you do, you set 4 is equal to 2. You take number 2, which is the partial of f with respect to y. So is equation number what? 4. Incidentally, when you take the partial derivative of this expression with respect to y, you get e to the x plus x cosine of y plus g prime of y. Why is this not partial derivative? Because it's a single variable. Do you see it? So when you set 2 equal to 4, you get this. Something nice happens. These guys nicely cancel. All you get is g prime of y is equal to 0. But remember, this is derivative of what? Y, um, with respect to y is equal to 0, correct? Derivative of g with respect to y is equal to what? 0. So take the antiderivative of both sides. Now, because this guy is a single variable, so g of y is equal to c. C is what? A real number. So now substitute 5 into 3 right here. So you have your potential function, but you have infinite many answers because it all depends what c is. Usually the problem is find a potential function, which means we only need one potential function. So it's customarily that or tradition, or it's practice that we set c equal to 0, and we get a potential function. So this is the potential function. So now with this, I can what? Do application problems, such as find the work done by the force. Now let's say the vector field, which we just found its what? Potential function was the force field to move a particle on the curve cosine comma sine from 0 to pi. So that would be like what? Quarter of a circle with radius 1. So I don't have to parameterize this anymore. I don't have to find the derivative of the parametric equation. I don't have to express this in terms of parametric equation of the curve. All I have to do, because the force we already proved is conservative, and that's why we found its potential function. So we evaluate this potential function at the endpoint, regardless of how we got from point A to B. So take that potential function, evaluate it at points A and B, which is 1, 0, 0, 1, and lo and behold, you have the work. So no mas, no fuss. Do you see it? So this is totally path independent. In other words, I could have gone from point A to B via this straight line, and the answer still would be 1 as far as the work is concerned. Because the force field is conservative, so the answer has nothing to do with the path. Do you see it? It's path independent. All right. So the question is now a follow-up, part C, to the same problem. Same vector field, force field, to move a particle on what? On the entire circle. Now the path is closed. We decided if the field is conservative and the path is closed, then what? The amount of work is 0, right? So, so what? So, provided you have a simple closed curve, so the amount of work is 0. Why? Because the initial what? Point of the curve coincides with the terminal side. So that's like as if you go from A to A. Do you see it? All right. Whereas in this case, we have to go from A to A or B to B. It doesn't matter because A and B happens to be the same if the curve is closed. In case of R3, instead of P and Q, then you would have P, Q, and Z. Then you would have a Z component. Okay. And the test for conservativeness requires that we what? Verify three proportionality. Partial of p with respect to y equals partial of q with respect to x. Partial of p with respect to z equals partial of r with respect to x. Partial of q with respect to z has to be equal to partial of r with respect to y. All these three proportionalities has to be true in order for a vector field in three dimension to be conservative. There is a much better, easier way to test the conservativeness of what? Three-dimensional vector field. Stay tuned for upcoming sections. Thank you.